Assalamualaikum warahmatullahi wabarakatuh. So today we are from Group 6. We will present about Metal Organic Framework. So my name is Fatimah Zafira binti Muhammad Aini. My group member is Aina Shazwina, Alisa Syuhada, Siti Nohanani, Muhammad Aidil, and also Ana Suhaili. So I will start my presentation with MOF structure. So as you can see from the slide, the illustration of metal organic framework consists of the metal ion and organic ligand. As you can see, the metal will bind together with the organic ligand. It's also highly porous material with a ultra high surface area. So I will tell you the detail about the structure after this. Next. Okay, now this is the characteristic of MOF structure. The first one, MOF are constructed by joining metal or metal cluster with organic linker, which is mostly they are carboxylic acid or nitrogen containing ligand. The metal cluster also called as secondary building SBUS. The two components can be recognized in the MOF is secondary building unit and organic molecule or linker. This is some representative SBUS and organic linker for MOF. Okay, the next characteristic is in each geometry variant, the central metal can be substituted, which is it can be replaced. In detail, the substitution is different of secondary building unit bind with a same linker. This means that different secondary building unit, same linker, and will lead to different MOF structure. For example, the synthesis of MOF5 consists of tetrahedral zinc oxide connected with terephthalate dianion. The second example, we can see MIL101 consists with a chromium connected same terephthalate dianion linker, but which is we can see the product is different but bind with the same linker. Okay, the next characteristic is the coordination number of secondary building unit can vary from 3 to 66. Can vary means that difference in size. Which is we can see the secondary building unit can be combined with a framework structure through different linker. The previous one, I tell you about different secondary building unit bind with a same linker. But this one, same secondary building unit but bind with a different linker. The selection and substitution of linker can lead to two situations, which is the first one is the symmetry is same with different linker with only unit cell parameter change because of elongation elongation of carbon chain. For explanation, the symmetry is same but different linker with only unit cell parameter. This is due to elongation of carbon chain. For example, we can see from UIO660 to UIO68. The figure show the framework symmetry same with increase in the linker change length. That what we call the unit cell parameter. Next. The selection and substitution can lead to situation of the symmetry is changed because of the change in the mutual arrangement of functionalities. This means that the change of geometry MOF, it depends on the mutual arrangement of substituent in the linker molecule. Thus, if there is a change, so the symmetry will be changed. As you can see the picture, the figure show the example of the change of geometry of MOF depend on the mutual arrangement of substituent in the linker molecule. The yellow sphere show the pores volumes. Okay, I will pass my presentation to Nani.
So I will continue the presentation with the metal organic framework chemistry. So MOF consists both organic and inorganic units. So the organic units, which is the linkers and bridging ligand, will consist of carboxylate or anions such as phosphonate, sulfonate, and heterocyclic compounds. The inorganic units is the metal ions or cluster, which is written as SBU. The geometry of the metal organic framework will determine by the coordination number, coordination geometry of the metal ions, and the nature of the functional groups. The variety of SBU geometries with different number of points of extensions, which is such as octahedron, which has 6 points, trigonal prism, square parallel, 4 points, and triangle. So this figure shows the example of organic ligands with carboxylic functionality that we use for the preparation of metal organic frameworks. For example, we have this is H2BDC, teratelic acid. We also have 1,3,5 benzene ethyl carboxylic acid, and some more. Okay, so this figure shows some of ligands which that can be used, like that containing nitrogen, sulfur, phosphorus, and heterocycles that can be used for the preparation of metal organic frameworks. For example, we have bipyridine, hexamethylene tetraamine, 2,4,6,3,4 pyridyl 1,3,5 triazine, 1,3,5 benzene triphosphoric acid, and 1,4-bis imidazole 1-imethylbenzene, and 1,5-naphthalene disulfonic acid, and also tetrakis-4-cyanophenylmethane. Next. In a principle, the bridging ligands such as ditopic, tetratopic, or multitopic linkers will react with a metal ion with more than one beacon or lebeside. The final framework topology of MOF is governed by both SBU connectors and organic ligand linkers. So depending upon the nature of system used, the extended polymerase or discrete closed oligomerase structures can be arrived. This figure 3 shows you the metal organic frameworks resulting from different metal nodes and bridging ligands. Okay, so for example, we have these metal nodes with vacant sites. And also the brigine polydentate ligand. So from this reaction, we can get whether it's 1 dimension, 2 dimension, or 3 dimension metal organic framework.
Okay, next I will explain the properties of metal organic framework. Metal organic framework is widely used due to its promising properties and in various applications. So the first advantages of MOF is that it has higher surface area and more volume compared to the other same applications such as zeolites, where MOF with high microforce volume and large surface area are desirable for storage, separation, catalysis, and drug delivery. And the pore size and the surface area of MOF can be increased by linear extension or elimination of the organic linkers. As MOF have a larger surface area than zeolites, it can be used as selective catalyst in different reactions, including reaction with bulky molecules that cannot penetrate zeolite pores. And a high surface area is beneficial aspect for high performance gas sensor. Example, MOF coated with an electrode that form an electronic sensor that could detect traces of sulfur dioxide gas. Next is the wide variability and composition of MOF. As we know, there is experimentally 10,000 known MOFs compared to only fewer than 300 zeolites. This is due to it has lower topological restriction on forming porous 3D framework, where it is invariant in stretching, bending, and squeezing, but not to bond breaking. So example for 4-connected network is it can form 3 different structure arrangement as pictured in the slide. Next is the electrical conductivity properties of MOF. As we know that MOF is built out of SBU, which linked by the organic linkers. This is made the MOF have low electrical conductivity. where it will be not suitable for energy storage and generation, chemical sensors, and photosensitizers. This is due to high electronegativity of oxygen atom in the carboxylates, where electron will require a high voltage to pass through the organic linkers, which result in poor overlap between oxygen atoms and metal d orbitals. So generally, MOF only have electrical conductivity of 10 to the power negative 7 to 10 to the power negative 10 Siemens per centimeter, where it typically will be used as an insulator instead of conductor. So the solution of this problem is that by using hybrid MOF, where the micropores of MOF will be integrated with the uh, conductance materials that can increase the electrical conductivity. And next is the strength and stability of MOF. Generally, MOF actually have low endurance and stability compared to zeolites, where it's due to thermodynamic factors, kinetic factors, and other operating environments. There is three types of stability components, which is chemical stability, where it resistance to various chemical exposure in their environment, example, moisture, solvents, acids, bases, and aqueous solution containing coordinating anions. For thermal and mechanical stability is the ability of MOF to preserve their structural integrity upon exposure to heat, vacuum, or pressure treatments. Next. So in a stability, there is three factors that govern its stability. The first is thermodynamic factors, which related to metal ligand coordination bond strength. In the synthesis of MOF, relatively high pKa ligand, for example, azoles, will easily produce robust, stable framework with low valent metal ions, while low pKa ligands such as carboxylic acid will tend to bind with high valent metal ion, which is a stable structure. And next is a kinetic factor, where the longer linker and larger pore size will lower the chemical stability. This is due to the kinetic factor which related to the rigidity of the linker, coordination number, surface hydrophobicity, and framework interpenetration. While dense and rigid framework, which built up by highly connected building blocks, will give higher stability due to high tolerance toward partial lattice collapse. And MOF stability can also be enhanced with surface hydrophobicity, which prevent the absorption of water into pores and condensation process around metal cluster in the presence of water. And next is the operating environments of the MOF, where MOF stability are varied depends on the condition of the operating environment. For example, for moisture labeled MOF5, it can only retain its crystallinity upon heating at 300 degrees Celsius in air for 24 hours. Next.
Okay, I will continue with my part, which is the synthesis of metal organic framework. Okay, so as you can see from the figure, the concept of MOF synthesis are where molecular building blocks, for example, this metallic cluster IBU and organic linker OBU are linked together into extended structures. Okay. So there are a few methods to synthesis metal organic framework. So why do we need different synthesis methods? This is because they may have a strong impact on reaction time, yield, particle size, and also the morphology. And it will also be differently well suited for the implementation in large scale process. Okay, so next, I will explain to you the methods. The first method is the conventional solvothermal method. Okay, so solvothermal synthesis is generally defined as a chemical reaction taking place in a solvent at temperature above the boiling point and pressures above 1 bar. The medium used in solvothermal synthesis can be anything from water, because hydrothermal, to alcohol or any other inorganic and organic solvent. Okay, so molecular organic framework have been synthesized solvothermally via conventional electric heating in small scale in vials or sealed NMR tubes under autogenous pressure. The operational temperature range is between 80 degrees Celsius to 260 degrees Celsius, which can be primarily affected by the cooling speed when the reaction ends. Okay, so next is the microwave assisted method. The conventional method just now is generally used. So therefore, the researchers have found there are alternative methods that can shorten synthesis time and to produce smaller and uniform crystal, which is the microwave assisted method, and also the other method that I will explain later. So this is the microwave assisted method. So in microwave synthesis, a substrate mixture in a suitable solvent is transferred to a Teflon vessel, sealed and placed in the microwave unit and heated for appropriate time at the set temperature. This microwave approach, where an implied oscillating electric field is coupled with the permanent um, dipole moment of the molecules in the synthesis, inducing molecular rotation, so it will result in rapid heating of the liquid phase. Okay, so in this method, besides the fast crystallization and also the potential advantages of this technique include the phase selectivity, narrow particle size distribution, and facile morphology control. Okay, next is the electrochemical method. Okay, so the electrochemical method synthesis uses metal ions continuously supplied through anodic dissolution as a metal source, instead of using metal salts which react with the dissolved linker molecules and conducting salts with the reaction medium. So the metal deposition on the cathode is avoided by employing protic solvents, and also in this process H2 is generated. The electrochemical route is also possible to run a continuous process to obtain a higher solid content compared to normal batch reactions. Okay, so the benefits of this method include avoiding anions such as nitrates from metal salts and slightly temperature of reaction and extremely quick synthesis compared to the solvothermal synthesis just now. Okay, next is the mechanochemical method. This reaction is carried out at room temperature under solvent-free conditions, avoiding any organic solvent. So there's a typo inside there. So there are three different mechanochemical methods used for morph construction. So first one is the neat grinding. This process or method which they avoid the use of any solvent in the process of the reaction. Okay, so the next one is the liquid assisted grinding, LAG, which is more versatile and quicker. It's a fast process as it uses catalytic amounts of liquid phases which increase the mobility of the reagents. Okay, and lastly is the ion and liquid assisted grinding, which uses a catalytic liquid with traces of salt additive to accelerate the morph formation. Last one. Last one is the sonochemical method. Okay, sonochemical method uses ultrasonic wave, as you can see from the picture. It is accelerated nucleation, can also achieve a reduction in crystallization time and significantly smaller particle size than those by the conventional solvothermal synthesis. Like I said, solvothermal synthesis is a very general synthesis that people use, but it takes a very long time. Okay, so a substrate solution mixture for a given morph structure is introduced to a horn type Pyrex reactor fitted to a sonicator bar with adjustable power and also without any external cooling. So formation and collapse of bubble form inside here after sonication. Term acoustic cavitation produce very high local temperature around 5000 Kelvin, around pressure 1000 bar, and extremely fast heating and cooling rates to produce a very fine crystalline. Okay, so I will pass to the next presenter.
Okay, next. Okay, hi, I'm Alisa. So I will present about application of MOP. So our group get gas purification and separation. Okay, so gas purification. What is mean by purify? Okay, to purify a gas means that to increase the concentration of the wanted gases and to reduce the unwanted gases, or what we call it impurities. Okay, so the impurities will be removed from gases through multiple purification material. So various material can be used, however, they are very selective, such as zeolite, activated carbon and MOF itself. Okay, so for example, to purify oxygen, the gas will be led through several purify material that each will remove a specific impurities such as carbon dioxide and moisture. Okay, so we can look at here as MOF as a purifying material. Okay, so MOF can be used to reduce moisture. MOF shown great potential for water absorption in gaseous media uh, as they are tunable to specific relative humidity level. Next, to reduce methane, a MOF called an alkyl MOF ATCCU feature methane capture capability for coal mine methane at 1 bar and room temperature. Means that this MOF can capture methane from the coal mine. Okay, to reduce oxygen, unfortunately, MOF have not been tested at scale yet due to its relative short existence. So, however, MOF have a great potential as they are very tunable to great selectivity and shown large uptake capacity. Next, I will pass to Anas.
Okay, for the gas separation, metal organic frameworks is used for carbon dioxide separation. Usually, aqueous amine-based absorbents are applied on large scale to chemically absorb carbon dioxide, which is highly energy intensive. However, with the use of metal organic frameworks in carbon dioxide separation is more energy efficient. Microorganic frameworks are perfect material for the capture and separation of carbon dioxide due to their high surface area, tunable process, and designable and controllable framework structures and topologies. MOF are greater carbon dioxide separation compared to zeolites and activated carbon. This is because zeolites have a limited number of crystal structures and carbon molecular sieve have amorphous structure. MOF, however, can form a vast variety of ordered structures, pore size, and porosities with functional groups from the different arrangement of metal centers and bridging organic ligands. Next. With this figure, we can see that carbon dioxide is absorbed more than other gases. This because carbon dioxide have higher polarizability and quadrupole moment compared to the other gases. Higher polarizability and quadrupole moment of carbon dioxide result in stronger interaction with the pore surface of metal organic frameworks, showing a great potential in carbon dioxide capture and separation. Next. Metal organic frameworks also used for sulfur dioxide separation. It can capture sulfur dioxide at very low concentration with very high selectivity. Hexafluorosilicate CIF6 based on MOF are used for highly selective recognition of sulfur dioxide. Sulfur dioxide interact strongly with CIF6 to carbon I, which resulted in highly efficient removal of sulfur dioxide compared to other gases. We can see the sulfur dioxide absorb more at the right figure. At the left figure is the structure of metal organic frameworks, CIF6 to carbon, CIF6 to copper I. Next is a reference for our presentation. Next, thank you.